e.g. 320 Structural Mechanics 3. Revision Notes, Part I, Stability. Highlight, key topics, concepts, procedures covered. Explain, difficult points to enhance understanding. TechSolve Hub. Aim and objectives of the module. Understand how structures can fail because of two failure mechanisms. 1. Buckling. Large displacement/deformation causes the structure to lose the load-bearing capacity, and or leads to material failure, structural failure. 2. Plastic collapse. Large stress causes failure of material points failure of sections of structural members to lose the load-bearing capacity collapse of the whole structure. Introduce simple analysis procedures to determine the critical or collapse load. Part I, Stability. Failure mechanism, buckling. Individual members of trusses, beams, columns have large deformation under compressive, or torsional, loading, but tensile loading cannot cause buckling. Global buckling, whole member affected. Local buckling, only local area affected. No material failure needs to be considered. Other thin wall members/structures can also have local buckling. Local buckling. Global buckling. Torsional buckling. Beam web. Shell buckling. Local buckling. Part I, Stability. Key concepts, stability of equilibrium and total energy. An equilibrium state can be further classified as stable, B. Unstable, A. Neutral, C. An equilibrium and its state can be determined using the total potential energy of the system. First derivative gives the equilibrium conditions. The sign of the second derivative indicates the state of the equilibrium. This energy-based approach is an alternative to the standard method that is based on Newton equilibrium equations, but is more general and convenient. It can be applied to more complex problems, and forms the foundation to the finite element method. Part I, Stability. Key concept, total potential energy. 1. Definition of total potential energy, TPE. Potential energy due to a force. Remember the minus sign, for V. Part I, Stability. Key concept, elastic, strain, energy of basic members. Torsion spring. It stores strain energy when subject to a torsion to undergo relative, angular deformation. Some students struggle to understand how a torsion spring works. Just check and play with a clothes peg to help you know its mechanism. Part I, Stability. Key concept, elastic, strain, energy of beam/column. Pure bending is the main deformation mechanism for beam. DLRD. Each infinitesimal segment can be viewed as a torsion spring, but the bending moment/deformation angle varies along the beam. Part I, Stability. Key concept, principle of total potential energy. Principle of total potential energy, TPE. First derivative gives the equilibrium conditions. The sign of the second derivative. It is very important to identify the correct number of independent displacements for a given structure. But there may be many options which variables can be used. Part I, Stability. Key concept, how buckling happens for a spring bar system. A spring bar system has one DOF, the simplest system. The bar is rigid. One DOF. Or can be chosen as the independent variable. The full behavior of the system when P increases can be analyzed by full geometrically exact assessment through delta, but for computing the buckling load, the second-order approximate method, P analysis, is sufficient. Part I, Stability. Key procedure, buckling loads for a 2 DOF spring bar system. The spring bar system has 2 DOFs. Follow the procedure below to compute buckling loads. Identify independent variables, there are many options. Find out their relationships. Assuming small deformation to simplify the derivation. Express TPE in terms of the independent variables. Consider all springs and energy due to the loading. Simply the expression. Make sure no algebraic mistakes. Otherwise you will get wrong answers. Use the equilibrium conditions to write down the two equations, and rearrange them in matrix form. Two eigenvalues of the coefficient matrix in terms of P are the two buckling loads. Part I, Stability. Key procedure, buckling modes for a 2DOF spring bar system. After two buckling loads are found from the previous steps, the corresponding buckling modes can be obtained. For each buckling load, substitute its value into the equilibrium equations, which will lead to two linear equations. Only one is independent. Arbitrarily set a non-zero value to D1 or D2. Use one equation to find out the value of D2 or D1. A buckling mode shows how two displacements will relate to each other. The actual values are not important, but their ratio or relative values. Always sketch diagrams to visualize the modes in exam. In general, the number of buckling loads/modes equals to the number of DOFs. Part I, Stability. Key procedure, buckling loads for a strut. The previous spring bar system can be considered as an approximation to a real column. There are two approaches that can be used to find out the buckling loads of a column subject to an axial compression. The classic Euler solution will give the exact buckling load, but needs to solve a second-order ordinary differential equation, ODE, and thus is hard for complicated cases. Rayleigh's method is simpler and follows the same TPE approach as in the spring bar cases. But only one buckling load can be found. It may be an approximation which would always be larger than the true value, unless a true deformation shape is used. Part I, Stability Key procedure, Euler's solution for buckling of a column. Establish the equilibrium, ODE, equation for the beam. Use the moment and deflection relationship. Specify the correct boundary conditions. Find the general solution of the second-order ODE. Apply the boundary conditions to the general solution. The existence of a non-zero/trivial solution leads to an equation that buckling loads should satisfy. For each load, the corresponding non-zero solution is the buckling mode. There are an infinite number of buckling loads since a column is a continuous solid. But only the lowest one has practical engineering meaning. Part I, Stability. Key procedure, Rayleigh's method for buckling of a column. The previous spring bar system can be considered as an approximation to a real column. Assume a deflection shape using a function with one unknown parameter. This function only needs to satisfy the boundary conditions. Better assumption of the shape will give better approximation to the true buckling load. Evaluate the integral to find out the expression for the shortening of the column at the top. Use small deformation assumption to simplify the integration. Further evaluate another integral to determine the strain energy of the column under bending. Part I, Stability. Key procedure, Rayleigh's method for buckling of a column. The previous spring bar system can be considered as an approximation to a real column. Write down the expression for TPE, plus equilibrium, the first derivative equals to 0. The non-trivial solution leads to the buckling load. The assumed deflection function is the buckling mode. The buckling load found will be the upper bound of the true buckling load. The accuracy of the obtained buckling load will be determined solely by the quality of the assumed function. Try more possible deflection shapes can improve the accuracy. Choose the smallest value as the final answer. Part I, Stability. Selected outline solutions to some HW exercises, slide number 43, A. Following slide number 34. Assume two DISP D1 and D2. TPE, assuming all torsional stiffness K. K2/2 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 Pu. 1 2. The simplified form in D1 and D2. K. 2 DD. 2 2D. D2 D2. PD2 DD. 2 D2. 2 L2. 1 2 2 1 2. 2 L. 1 1 2 2. Equilibrium. D1. 0. 0. D2. In matrix form. 15K4K2. 1D10. LL. P. L4K6K. 12D20. LL. Initial stiffness term. Initial stress term. Try to assume different torsional. The two buckling loads, P. 1 equals 1.4514K/L, P. 2 equals 3.2153K/L. Stiffnesses for the three springs, and repeat the analysis. The two buckling modes, V1 equals 10.8229, V2 equals 1-1.8229. Also try to use other options for two independent displacements/angles. Part I, Stability Selected Outline Solutions to some HW exercises, slide number 43, B. B. Note the, added, middle linear spring stiffness equals 8K/L2. Assume 2 DISP D1 and D2 as case, A. TPE. K2. /2 K2 K2 K2. /2K, D. D2. /L2 PU. 1212. The simplified forms of U and V in D1 and D2. UK3D D2 3D D2 3K, D2 D2, 2K DD. 4L2. 1221. 2L212. L21. VPUP 3D2 2DD 3D2. 4L1122. Equilibrium conditions and in matrix format, fill the gaps below. The two buckling loads, P. 1 equals 4.5K/L, P. 2 equals 7K/L. The two buckling modes, V1 equals 1-1, V2 equals 1-1. Try it yourself, follow the example on slide number 40 and add a torsion spring as case, A. Part I, Stability Selected Outline Solutions to some HW exercises, slide number 60. Let the displacement at x equals L be. The moment at position x is, MP, V. The, bending, equilibrium equation is D2V. 222. MEI dx2. P, V, VV. P/EI. The boundary conditions are V, 0, V, 0, 0, V, L. The general solution to the above equation is V, x, a sin, x, b cos, x. Where a and b are two constants to be determined. Apply the three boundary conditions to leads to PCR 2EI 4L2 V cos x cos L 0. The corresponding buckling mode. For a non-trivial solution 0 cos L 0, so V11 cos x/2L L and 1/2 and 1 2. Assuming the above is the deflection shape and apply Raleigh's method to see if you can get the right buckling load.